Morning all. You know, I actually have done Friday mornings a few times and, you know, the attendance has always been a little down. So this is the same thing. So this is just between me and you, right? It's a little secret. Everyone else, you know, tough. You missed it. Too much drink. I've spoken at AusNOGs for ages and, you know, most of the time I've become old and cynical. Don't ask me about V6, you don't want the answer. Don't even ask me about RPKI, you don't really want the answer. And as for the internet of trash, you know, we're all doomed. But there's a few bits and pieces which technically are amazing, just truly amazing. It's like Bevan saying, well, fibre optic is actually a massive microphone. Holy shit, you can hear whales. Well, what I want to talk about today is one of these engineering things which are just stunning. You know, think what you like about Elon Musk. We all have opinions. I know I do. But, oh my God, this stuff is truly astonishing. It's taken the world by storm. The last time we tried it with Motorola doing Iridium, 15, 20 odd years ago, all the world's mobile carriers that were just going, oh my God, the threat from hell, they'll take away our business, you know, we'll be broke. Telstra, you know, all the Americans, all the Europeans, oh my God, this is terrible. This time, they're jumping over each other to try and do the deal. In Australia, both Optus and Telstra have actually done deals with Starlink. It's happening in Asia, it's happening in most countries, because all of a sudden, this is not a threat for most, it's actually an amazing opportunity. This shit works. And it's kind of, why? How? Okay, so I want to do a little bit of physics for you. Isaac Newton, Sir Isaac Newton, noted astrologist, noted loony, but came up with some amazing physics at the same time after he'd, you know, beaten his head around with this thing called calculus and figured out if you could weigh the Earth, and he kind of did, and knew about gravity, which he kind of worked out, that if you could take a lump of anything and throw it up at a little more than 11.2 kilometres a second, it'd never fall back to the Earth. It was just out there, and it was never coming back, because you're beyond escape velocity. Nice experiment thought. But then if you get on top of a big mountain, and instead of throwing it up, you throw it sideways, it'll never actually go back to Earth. It'll just sit there in orbit. And if you're above the atmosphere, there is no drag. No drag. It'll just go round and round and round. And you don't even need station fuel because there's no drag because you're above the atmosphere. So if you push it up high enough, it'll just stay there. And at the time that was kind of, well, that's cute, but so what? You know, you need a lot more technology to actually make it work. Now, there's another bit of technology in which, you know, the rock we live in is kind of golden. There's another rock a little bit out that way, Elon's keen on it, silly bugger, called Mars. And the problem with Mars is that it's just not big enough. You know, why not? You see, the Earth is big enough that the compressive gravity force keeps the solid iron core molten. That allows the bloody thing to rotate. Do you remember physics? Rotating conductors, magnetic field, solar radiation. So while Mars didn't, because when its core stopped rotating, solar radiation blew its atmosphere away, and if there were Martians, they all died a horrible death. You know, it was all over. Water evaporated, that was it, you know, Mars, whoop, sorry. And the Earth, because it's still rotating, the Van Allen belt deflects away solar radiation. We get to breathe, which, you know, is a biological carbon thing I'm really thankful for. But as well as that, it creates this massive shield around the Earth, the Van Allen belts. And most of that solar radiation, which is incredibly high energy, doesn't actually hit the Earth's surface. And if you think about it, and that's what that diagram shows, even if you go up into space, you don't actually get that radiation. It's only when you move beyond the Van Allen belt and you take biology with you, thank you astronauts, you actually need, you know, lead-lined BVDs, the lot, because it's very dangerous stuff. But down low, You can actually take advanced electronics and not have them completely shredded by solar radiation, which, oddly enough, is where LEOs live. LEOs live in that fascinating area. Australia owns, I don't know how deep. Does it go to the core? We certainly claim we own all the minerals, and we own the air above Australia, but it's the air. Most countries claim that up to an altitude of 100 kilometres, it's ours. But beyond that, it's outer space. It's nobody's. And once you get above that space, 160 odd kilometres, you are in outer space, no laws. And that sort of magic area just below the Van Allen Belt's sort of major barrier between 160 and 2,000 kilometres is what we call a low Earth orbiting area. So you can actually do decent electronics. I need better glasses here, or this screen needs to be bigger. You can actually do decent electronics. You're above the atmosphere in almost everything except massive solar radiation. When you get massive solar radiation, the atmosphere inflates, all that energy, and you start grazing. But thank God that only happens once every few decades, I hope. So does Elon. And above there, you're kind of in this sweet spot. So Elon Musk has launched at 550 kilometres, thankfully 100 kilometres above the space station, or they'd all be dead. You're kind of circling the Earth. Now, in space terms, that's really close, really close. Speed of light over 550 kilometres and back, 3.7 milliseconds if it's straight above you. There and back is really, really fast. It's like a trip down to the shop with fibre. It is honestly quick shit. Now, what Starlink did was launch up at that space, and when you look down, right, you see a part of the Earth. Now, the minimum inclination is 25 degrees. If you went lower, the Earth's microwaves, all those folk doing microwaves yesterday, lining up mines and so on? If you're too low, there's a microwave straight at you, no one's very happy. So as long as you keep your minimum inclination above 25 degrees, you avoid all this terrestrial crap, and you're kind of looking up. And you can't look up at the geostationaries, same frequency, bad idea, but there's a kind of sweet spot between 25 degrees and straight up, the equatorial band, where you've got a huge amount of space. Now, when it looks down, what each spacecraft see is a circle with a radius of around 950 kilometres, or 2 million square kilometres if you're that way inclined. If you had exactly 500 of them, and somehow you space them perfectly, you only need 500 to cover the entire Earth, right? So if you're moving around, if things are a bit sloppy, you'd probably need about 6 times that, or about 3,000 to 5,000 spacecraft, and you've covered the entire Earth. How many has Elon launched? Ooh, about 5,000 so far. That's at one plane, 550 kilometres up. He has filed, and whether it's just to keep the Chinese nervous or if it's real, he's filed to actually launch another 25,000 at 2 more levels of altitude. This is the great race to occupy the space before anyone else can get there. Why is he serious? Because thanks to NASA, he got billions of dollars to do the one thing no one else could do. Take a rocket, push it up there, that's the easy bit. Turn it around and make it land on its ass and use it again. Not even the space shuttle got anywhere close. They can reuse the rockets within a cycle time of a few weeks, not, I think, what was NASA's space shuttle, 9 months? All of a sudden, the cost of putting crap up there, which on conventional rocketry was around $1,800 to $2,000 a kilo, is below 700 and falling. He is cheaper than anyone else by about three times. Jeff Bezos has either got to reach into the checkbook and make Kuiper work at a loss for years, or try and figure out how to make rockets land on their ass, because only Elon's managed to do that. And while he's doing that, he's kind of in a monopoly position, because unless you're a government, you can't afford to compete with that kind of economics. So that's why there are so many being launched. This is the great, Western land grab for all of that low Earth orbiting space. So they're interesting. You don't need a crap load of power. They're just up there. They're really, really, really close. Even handhelds can indeed make some kind of connection. It's not the best, but it can. Oddly enough, we're good on radio. The whole 4G, 5G work actually said there's a huge amount of knowledge on how to make these kinds of signals sing and dance. And so you get actually very, very high signal speeds. And there's nothing out there. There's no buildings, there's no one else, there's no microwave, there's no other infrastructure. It's just up there. So, launch cost low, interference low. Once you're there, woohoo. So they're interesting. They did one more thing that Iridium 20 years ago failed to do. Because up until Starlink, these things were what the rocket boys call bent pipes. It's just a bloody great mirror in the sky. You aim your signal up, it comes down. And if you think about how low they are, down has to be within 1,800 kilometres of you, right? Because that spacecraft only sees a circle of the Earth. So if you actually want to cover, I don't know, the Simpson Desert, you need a base station there as well. You need fibre infrastructure, blah, 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 blah. Nah, never going to work. But he has got lasers, space lasers. I'm like, so cool. Now, the thing about this again is you're launching a lot of spacecraft and they're in trains. There's always one ahead of you and one behind you in your orbital plane. So you don't need to steer the laser. If you're traveling on this spacecraft, it's just there in front and it's just there behind. The lasing is now easy, relatively. And so he uses, I think they're 100 gig lasers. Interference, power, just aim away, there's nothing else out there. And so the architecture kind of says, you can be anywhere, and if there's no Earth point near you, you go up and over and down. In Mongolia, where they're now selling it like crazy out on the Great Plains of Mongolia, they reach the terrestrial network in Japan, up, over and down. You're in space. You are travelling at the speed of light. Unlike fibre, where you're travelling at 2/3 the speed of light. It's oddly enough faster for the signal. Faster. And so in some ways, this stuff is actually astonishingly clear and astonishingly good. And the folk behind these things in Mongolia are probably getting better service for some stuff than you ever got on any terrestrial infrastructure. So again, lasers were the one thing that kind of changed from Iridium, that and just a truckload of bandwidth that make it all different. But it's not without its challenges, right? When you stand and look at this crap, you see this sort of thing slowly moving across. Horizon to horizon, 5 minutes if you're patient. But it's 550 kilometres up, so it is travelling at 27,000 kilometres an hour. This is like using a mobile phone in a car against a fixed base station, if you think, but you're travelling at 27,000 kilometres an hour. Jet planes, nothing, they're just static. This is fast crap. So tracking it is kind of interesting. I did this actually using some space software. There's some awfully good libraries of this stuff. And this is, if you looked up, and in this case I'm looking up in California, and you accelerated time by about a factor of 10, this is what you see. This is what you see, a whole bunch of these things. And there are a couple of trains which I really like, because he launches them in trains, and then over time they gradually space out and evenly distribute. And so at any point on the Earth's planet between, 50 degrees latitude north and south, you'll see between 30 and 50. Tasmania, well south, they all come together, so you see more. Underneath, say, Papua New Guinea on the equator, you only see about 30 because it's bigger there, right? They're further apart, and as they come together at the poles, you see more. Each satellite goes across this visible aperture of 25 degrees for a maximum of 3 minutes. Imagine if you're using the old form steerable dishes. You burn out the motor in seconds. So there's a bit more going on here. The first thing is you don't track it for 3 minutes. You track each spacecraft for just 15 seconds. 15 seconds. And you switch to another. The second thing is they borrowed some stuff that the military were really cool about, which is phased array focusing. If you listened to Bevan yesterday, that's what he does on the fibre with those signals. It's phased array work. So he gets 11 degrees of arc tracking using electronic focusing, and that's what's inside the magic of the dishy. So you get assigned a satellite, 15 seconds later, another satellite, another satellite. The satellite itself, well, it uses 2 gigahertz of spectrum in the Ku and Ka bands, I think. Splits it up into 8 channels, each of 250 meg. 3 downlink, 1 uplink, 8 beams, 2 polarizations. That's 48 beams down, 16 up. It's not symmetric. It's built for what we do, sucking video, I think. Heavily towards just beaming the stuff down. 1/3 of the capacity is lifting it back up again. And if you think about it, here's this kind of phase of lights. Now, if you're on the Earth and you're sort of underneath it, what you'll see is it gets brighter, it gets dimmer, it gets brighter, it gets dimmer, it gets brighter, it gets dimmer. And so the signal-to-noise ratio is constantly varying. Remember that, because that's really important, right? Because that's kind of the key in making this stuff sing and dance. Some of you have this stuff already, and I'm sure when you've looked at the reports that come out of your dishy, you see this downlink throughput, uplink throughput. And if you sit there and go, refresh, 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 you actually find it's never the same number twice. Never. Because what's going on is they borrowed from 4G and then 5G, and they use adaptive signal encoding. So they're in Fourier space, they're doing phase amplitude modulation. But unlike, you remember analog modems? You remember the screech? So you sit there and test Fourier space, and then you go, right, that's it, I'm going to send it 32.3 kilobits per second, and I'm going to nail it for the call. I'm never going to test it again. Starlink tests for pretty much every packet. Holy shit. And as the signal-to-noise ratio changes, the link capacity changes because you're changing your coding. So the coding is constantly varying. This is the reason why DSPs have got so brilliant, that they're actually able to code and decode a constantly varying constantly varying signal encoding over a constant carrier. So it might be 250 megahertz, but you're actually getting a highly variable sort of bits per baud because of that adaptive coding. So that creates some really interesting things that you've never ever seen before in network engineering. On the left, if I've got this right, is available capacity. Now, that's as Starlink reports it. It's like a piece of wire that constantly changes its dimension every time you push a packet through. And it changes between 50 megabits and about 300 megabits per second as you push packets through. There's no constancy. There's no, well, I'm going as fast as I can go, because it's not like that. There's no fixed upper ceiling for protocols like TCP to bump into, because it's this constant fluidity that the actual capacity of the circuit is throbbing like you've never seen before, up to more than 75 times per second. But the other thing about this is you're now stressing your encoding systems, because as you constantly try and adjust to make optimal use of that signal-to-noise ratio, it takes time. And so bizarrely, even though that thing is 7 milliseconds away when it's right above you, and 17 milliseconds away even when it's sort of at 25 degrees, there's this added kind of problem of signal encoding. How long did it take your cheap, shitty modems to encode a packet to put on the copper? Does anyone remember ping times? I do, 5 seconds. Because it was crap processing. Most of the delay in dial-ups was actually in signal encoding. Same story. That a huge amount of that imposed latency is all about the fact they're doing some really wacko shit to actually try and get as much as they can through. So what you see is a latency that is just totally unstable. There's no round trip time. The scale on that, God, I need better glasses or an atomic microscope. Generally varying between between 20 and 50 milliseconds all the time. There's no stability. So why is this so noisy? This is the next one I was doing. You ping like a mad person. And this is the result of pinging like a mad person. But what I'm doing is then charting the ping latencies. And what you actually find is the upper level is kind of, yeah, right, it just takes more time from time to time. But look at the lowers. At every point, for precisely 15 seconds, and I mean precisely down to the millisecond, you get a different low point. And what that actually means is that you can see Starlink control is assigning you to a new spacecraft every 15 seconds. And it's not 0 second, 15 second, 32 second. No, no, no. It is 2 seconds past the clock tick, and it's not 2.3 or 2.5, it's 2. It's 17, it's 32, it's 47. And those are the switch points where you actually find that the bottom latency changes. Now, have you designed a TCP protocol where it's trying to optimize its behavior and fill the channel, and the channel's going, no, 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 no. I'm sorry, 15 seconds have elapsed. New variables, new minimum latency, new channel to try and optimize against. Oh, Christ, let's do it again. Down the bottom is loss, because that change is a bit catastrophic. I was pointing at A, the ground station, and we're having a fine old time, and now I've been assigned B. What happened to the packets that were in flight? You know, how do I make all this work? Well, as far as I can tell, what actually goes on is the phased array kind of splits. One half starts tracking the new spacecraft, and then you do half a hard switch. But you need buffering for the packets that you'd sent just to make sure you might need to resend. And what you actually find is that packet loss occurs when you get scheduling. So every 15 seconds, if you're going to lose a packet, you lose a packet then. Have you ever used circuits where every 15 seconds you lose one packet? Yes. How did TCP perform? Like shit. Because, oh my God, packet loss, I'm going too fast, that's congestion, back off. All right, let's go back in, packet loss, oh God, let's do it again. So this is kind of catastrophic. Non-congestive loss, as anyone in radio will tell you, is kind of murder on protocols, and Starlink kind of specialised at it because that's the nature of the beast. So if I remove the latency flicks, and you see the thing on the right, also what you see is at the time of handover, not only do you get loss, but you get this massive latency. It's as if you're using a massive queue that fills on one packet, which again is anti-TCP. That's not meant to behave like this. That every 15 seconds you get this sort of stretch on latency up to, you know, around 100 milliseconds, because that's what's going on in handover. Wow. So what I've got is a constantly varying baseline, but there's no protocol for Starlink. You're using the same old shit you use everywhere else. You know, oh, I'm doing Netflix video. That uses some kind of, I don't know, UDP-based or TCP-based. Oh, I'm doing the web. Oh, I'm doing Quick. You don't use a Starlink protocol. No one knows Starlink is there. No one knows there's Wi-Fi in the loop. No one knows you're using 4G or 5G. Same with Starlink. So you could build a protocol for Starlink, but there's all this other bits and pieces in the way between you and what you're talking to, you and the server. So the protocols we use are basically generally congestion-based, tail drop loss. The theory of TCP is I'm in a wire. The theory of TCP is it's as constant as shit, and all I'm trying to do, because I'm a greedy bastard, is take as much of the wire as I can while still be basically friendly to everyone else. And the way that works is the wire is constant. The road has a constant amount of car capacity, and I'm just trying to get my fair share. Starlink says, no, 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 all wrong. There is no constant capacity. There is no constant delay. There is no target to try and equilibrate against. You're on your own. That makes things fascinating. This whole issue about varying signal to noise, you're never going to make Starlink better. If you want to squeeze bandwidth out of Starlink, you have to cope with the fact that those channels are constantly changing for every packet. So it's a very, very fluid flux. And ACK pacing, which is what we've been using, doesn't work very well. Secondly, it's not your channel. It's everyone's channel. Starlink is the first, I think it's the first, I think even VSATs were more wholesale, that is retail. Retail. It's not a circuit. They never pretended to compete with the telcos. You are fighting it out with everyone else who's using your area of Starlink. And the more people who sign up, the bastards, the worse my service runs, the bastards. You know, you really want to go out in the middle of the Simpson Desert and be the only one there and shoot anyone who comes near you, because this is my cell. Piss off everyone else. Generally they use very conventional multiplexing, 750 frames per second, each frame 302 intervals. Basically it's a header, you know, a bit of encryption just to make sure that I'm talking to the right thing, and off you go, frame-based transmission. So I think I've hammered enough the whole idea that is varying systems of latency, of delay, and even of loss, where we've got a constantly shifting sands, and we've got contention. As soon as you start doing some massive video download, if I'm sort of near you with my dishy, both of us have a problem, right? So how does it work? Here's speed test. Now, speed test doesn't send data. It sort of sends the headers and tries to interpolate from that what the bandwidth would be. So this is Starlink in California, measured over, 9 months or something. He's been selling, but has also been launching. And even though there are more people, because terrestrial infrastructure in Silicon Valley is shit, and AT&T are indeed bastards, he's been launching more than the folk buying up the service. And over time, speed test is actually showing visibly better performance. It's not brilliant. Speed test kind of says, 100, 150-ish. And this is kind of a test every few minutes, just constantly. Geez, I'm running out of time, sorry. I'll go really fast. Now hopefully you're over your hangovers. Concentrate. I've got these flow control protocols. They're trying to figure out how fast to go. You've got classic loss-based, cubic and similar, which probe upwards, have a problem with loss, come down. And then I've got things like BBR that says, bugger that, I'm just going to figure out what the link's going to be, and I'm just going to run the blindfold and run it anyway. iPerf3, cubic, 40 seconds. Oh my God, it really doesn't work very well. Round about 50 megabits per second tops. And this is sort of one snapshot. You can see a bit of the congestion behaviour, but it's not brilliant, not brilliant. BBR, 200 megabits per second going up to 250. Why? Because BBR is not loss sensitive. The real answer is, if you really want your networks to sing and dance, convince the servers out there to run BBR for everything. The result might be kind of weird, but as far as I can see, BBR is the mammalian protocol. Cubic is indeed out with the reptiles. If you're running cubic, you lose. Tough. Even Quick, because Quick is based largely, most implementations on cubic, Quick is the blue, is actually worse than cubic in this test. It's only BBR. Now, BBR is noisy, but it delivers approximately between 6 and 20 times the flow capacity of a cubic flow. If your business is shipping data around the world and you're not using BBR, go get another job. Just go away. You're not helping, because basically protocols have moved on and loss-based congestion control is kind of reptilian. So to sum all this, like I said, I really am flying fast. I hope you're with me. Starlink kind of has these issues of really high jitter. We've never encountered that before. It has micro loss. Never really encountered that. Non-congestive based loss. Not even radio has that kind of signal. And you've got this bearer contention between users. There's no guaranteed channel rates. So things like cubic, the traditional way of sharing a common medium by end-to-end flow control, which we've been using for 30 years, doesn't work very well. Just doesn't, because Starlink puts up a new environment. So, those loss-based systems work fine when the signal itself is self-constrained. voice. I won't go video because video bursts hard, but even things like Zoom, they're not bad. They'll work well without any particular engineering because it's the sender that's constraining. But if you really want to shovel data through the link, not a good idea. You need to move to flow algorithms that are much, much better at going loss, I laugh at loss. I'm just going to send through it and just, figure out what the link should be and just press on regardless. Fair queuing. If you haven't enabled fair queuing and you're a data sender, what rock have you been living under? Do not burst, ever. The whole thing about bursting is you stress out everyone, including network buffers. Now, some folks say the answer is buffer bloat, you should reduce the amount of buffer space. I'm sorry, that's the wrong end of the problem. If you're listening, Dave, it's the wrong end of the problem. What you should be doing is pacing sending. Equally space what you send into the network, and you will never even need buffers to adapt, because fair queuing actually works far, far better in shared networks than any other mechanism. If you're not using selective acknowledgement, again, what rock have you been living under? Get with the strength and just go and do it. And widen that window as far as you can, because you need to treat loss as something repairable at speed. Whoops, stop everything, I need to repair a packet loss, is no way to run a modern network. And the only thing going around now is Apple's L4S setting up the network to signal the onset of queuing. An explicit congestion modification is kind of an ongoing debate. BBR is saying, and it came from Google, so it's no surprise, I give up on these network operators, they're banging the rocks together, they're living in prehistory, they're never going to get there. I'm going to design a protocol that I don't care what you're doing, I will avoid stressing out your network. ECN kind of goes, I'm a new enlightened network, I will mark the onset of queuing to give a hint to the non-BBR-like protocols that there is something to do, that they need to back off. So Apple, oddly enough, in conjunction with a number of carriers, has gone down this L4S model of getting the network and the end systems to cooperate. Google said, I'm sorry, you guys just don't get it. I'm going to solve my problem irrespective of the network. It's an open question as to which is better, but as you can tell, I kind of think Google's going to win. Getting other people to do things for you for free is always difficult. So what does it mean about Starlink? If you're just doing short transactions, if you're just doing video, if you're just doing talking and so on, Starlink is fine. And even for things like Qubit, you will get between 30 and 50 megabits per second pretty constantly, no matter what. As long as not everyone in your street, everyone, because you're competing with them, sign up. Rural or remote, fantastic. Just here in the CBD of Sydney, you are dreaming. Don't even try it. Because if everyone does it, you will die. But for the certain specialised areas, which Australia has a lot of, brilliant, nothing wrong with it. You can get 40 to 50 megabits per second, no sweat. And if you know what you're doing, I could compete against what we heard yesterday from OpenSky and give them a 300 megabit channel using BBR and Starlink for $300 a month for 3 sites. Holy shit. This is kind of what we're facing now with this revolution in LEO services, that terrestrial systems really have to redefine their economics in order to make it work. And as someone was saying to me before, yesterday, about the poor folk in the Solomon Islands, because it's everywhere. Why would you drag a fibre there where I can offer gigabits on Starlink? Because there aren't that many people living there. It's not the CBD of Sydney. You can make it work from Starlink and not bother with fibre. So if I want to bring out fibre, who's going to pay for it? So last time, the carriers killed Iridium, stone dead. It was bankrupt within a week of launching the final satellite. A $30 billion project got sold for $30 million in the bankruptcy courts. It's still there plugging away at 2.5 kilobits a second, whoopee-doo. This time I think Starlink is actually winning and actually slaying a whole bunch of marginal terrestrial. It is really, really interesting. And for that reason, I wouldn't build trunk infrastructure. There's not enough bandwidth. There just isn't. Fibre carries terabits, this stuff carries gigs. That's as far as it goes. But beyond that, for all of the Simpson Desert, for all of the yachties out there all over the world, yay, this stuff just flies. I've got about 30 seconds and one question. Be quick. Right, you're too slow. Thank you very much.